All right, so we are looking at uh, the special relativity section in the Physics 12, right? So what we're first going to be taking a look at is well, let's look at our learning goals here today. So we got to understand the concept of an inertial and non-inertial reference frames and the implications that it has on our understanding of light, okay? Um, and then we just have to explain the difference between these two. All right. So here we've got inertial frames of reference. The definition for them is that all things are a frame of reference is basically sort of like a point where you're going to be measuring things from, sort of like the location, the guy who's holding the measuring the device, more or less, right? And the guy who's holding the equations and manipulating the equations and sort of doing all of the calculations to predict certain things, okay, motion and stuff like that, right? So up until now, we've been basically dealing with inertial frames of reference. And basically what that means is inertial frame of reference is something, it's a frame of reference that's stationary or with it moving along. If it is moving along, it's moving along at a constant velocity. So the classic example is moving along in an automobile at a constant velocity. Excuse me. At a constant velocity, and like flipping a coin, and then the coin, or tossing a ball up in the air. And from your point of view, let's say you're in a limo or something like that, limousine, and the windows are all blacked out and you can't see anything. And you're on like a really super smooth road, and you're just driving along straight at a constant velocity. You throw something up in the air and it moves as what you would expect, has the same style of motion that you would expect the on the earth, or just like standing out in like a garden or something like that. But then if the so that would be an inertial frame of reference. Basically, the implications is that all of the physics formulas we've been using and sort of building throughout these entire sections here would work. Okay, and basically the idea is that if you're in an inertial frame of reference, there's no physics experiment that you could do to determine the velocity of your frame of reference. Okay, without no physics experiment that's confined to within your frame of reference, right? So imagine you're in an airplane, same thing, and you have your airplane is moving along, all the windows are blocked out. You're sitting there, all by yourself, and you have no communication with the outside world. There is absolutely no way that you could determine the velocity of the airplane from within the airplane. If that's the case, that is an inertial frame of reference, okay? Now, non-inertial frames of reference, okay? Newtonian physics, however, stress these okay, so I won't read all this to you. You can read this yourself. I'll send it to you as well. So you've got these non-inertial frames of reference. It's a pretty big thing there, so you can pause the video and read this. Okay. Non-inertial frame of reference are where this is not true. Okay. And so where you are actually accelerating. Okay. So for example, we are in this airplane, and then all of a sudden this airplane begins to accelerate forward. You feel like you get pushed back into your seat. Okay. Now, the interesting thing about non-inertial frames of reference, you actually can, from within the frame of reference, measure the rate of acceleration of this frame of reference. And so one way of doing that is to hold up like a string with like a coin or something on the end of it. And then based on the angle of the string, right, how much it's being pulled backwards, based on that, you should be able to measure the acceleration of that. And that we learned how to do that way back in section 1 in the kinematics section. We talked about that for a little while. So that's one of the things about non-inertial frames of reference. Okay. Anyway, so you got all that going on, and so this talks about different. So the thing is though, you would expect if you're holding up this string and the coin gets pushed backwards, there's really no explanation for it. Let's say you're in this airplane, you're just sitting there. This all of a sudden, you feel this force that's sort of pushing you backwards. There's no explanation for it. Like, why is this? Why is that happening? So what happens is scientists have made up fictitious forces, they're called, that explain the acceleration of the frame of reference. Okay. And there's one of them called like the Coriolis force. Then there's the centripetal acceleration or the centrifugal force, right? Or centripetal force. Sorry, that's not really the thing, but it's kind of like if you're turning in a car, you've got that force where it's like you feel like you're being pushed to the outside of the car, right? If the car turns right, sorry, I guess I'll go. Yeah, if the car turns right, you as a passenger feel like you're being pushed towards your left by some mysterious, mystical force that pushes your whole body, Anyway, that's not really a force. It's just actually your own inertia. That's actually telling you to go forward, but this car, for whatever reason, is turning the other direction. Okay, and so therefore, from within the frame of reference, you invent this fictitious force, right? That apparently pushes you to the other side of the car. Okay. Anyway, so that's how we explain these phenomenon of an accelerating frame of reference. Okay. So that being all said, right? This is where are we at here? Let's go down to this one. So, that being said, let's now go back outside the car here. And if you've got a ball, and you throw it forward in a car, the velocity of the ball from outside the car is going to be equal to the velocity of the car plus the ball itself, right? And so you can add two velocities based on the fact that the frame of reference is moving. Okay, you can add the two velocities based on the fact that the car itself is moving. So the velocity of the car plus the velocity of the ball equal the velocity of the ball to someone outside. Okay, so then you would say, well, that makes sense. Let's do that. And so now all of a sudden enter light. As it turns out, light does not behave this way. Okay, so this appears to be a violation of Newton's laws. Okay. And so the idea is that if we shine a light forward, and a car that's moving, according to this example, is 20, then the light that, if I'm now standing outside of the car, the person inside the car will see the light moving at the speed of light away from them. The person outside the car would see the light moving away from, moving across the screen or whatever, at the speed of light plus the speed of the car, right? So let me go ahead and draw this, I guess. So I've got some kind of car, top view here, top view of the car. There's somebody here and there's somebody here, right? And, this person is standing here and looking in that direction. And this person is standing right inside the car, right? Now, this car comes by like this, and they do like a flash of their headlights. Okay, like that, and their headlights go out, right? Well, let's just put a single vector to not complicate our things. So then you've got your speed of the light, right? Now, this guy would be like, okay, so the light travels forward at the magnitude of this vector, which is the speed of light. We'll call it c, okay? And now this guy, now don't forget, the car itself is moving at some other velocity. So now this guy says, well, I see the light. I'm going to go look at the light. And from my opinion, is moving at the speed of light plus the speed of the velocity, because plus the speed of the car, because the light emerged from the car while it's moving from my perspective. But there's an issue with this, apparently. The problem with this is you've got now two observers that see light traveling at two different speeds, okay? And so, therefore, not going to happen. Apparently, it doesn't happen this way. Both of these people see the light traveling at the speed of light, apparently. That's what ends up actually happening, right? So there are experiments that have sort of verified this to be true, okay? So then you might say, well, why is it that a ball would have 20 plus 3, but light won't, all right? And so it has to do with some stuff called the theory of relativity, okay, which we're going to talk about right now. So here, we'll talk about that in a moment, the theory of relativity. And then, but what I wanted to do is I wanted to first talk about a little bit here is the idea of measuring the speed of light, right? So there are these guys who did an experiment where they sort of shot some light and then separated it out in like a mirror. So some of it went through and some of it went like this, right? And then it would bounce back. Let's say that this guy bounces back and here, and then bang, bang. And now we have essentially, and then they measured how long it took for the light to reach these two locations here, okay? And so as a result, you end up with, different values. I'm gonna make this. Sorry, no, you don't end up with different values. Sorry, you end up with the same values. This is black light, so this is a combination of the two. Okay, and there you have it. So basically, what's going to happen here? This is also a combination of the two, right? And so basically, what's going to happen here is you can kind of see that this light here, this red light, okay, traveled sort of north and then south, whereas this green light traveled east and west, all right? And so what they've done is they've basically separated the light out so that one travels perpendicular to the other. Then they said, okay, well, what we're on the Earth here, and the Earth itself is moving in that direction, okay? So the question is, due to the fact that the Earth is moving in that direction, does it make a difference? Does it make it so that the light travels faster or slower in this red direction than it does in this sort of green direction? And they discovered, it turns out, that it does not. It has absolutely no bearing on the velocity at which the light, so these two beams of light end up landing there at the same exact time, right? You might say, well, how do they measure that? It's based on the frequency, right? It's the frequency that they emitted the light, right? They would expect the frequencies maybe to be coming in here, and it would be sort of out of phase versus in phase. And so they were going to expect some kind of destructive interference or constructive interference, actually, either way, based on, remember what we learned about last unit, right? So they were kind of wondering if maybe, you would get a compression of waves here, and then the waves would be longer here. And so then as a result, you would get like a compressed wave and a longer wave. And then as a result, you would have some sort of interference here that would cause you to see these dark versus light spots, right, in the light. But as it turns out, this did not happen, and they were they realized that the light ends up coming back at the same frequencies. Here, I'm trying to have some troubles here. Same frequencies in both cases. Okay, so they concluded that the Earth itself, it's the motion of the Earth through space, has no effect on the light and its velocity, right? And they were thinking that the space itself, they were calling it ether, right? Kind of scenario, right? So that's what they were kind of saying. It's like, well, if, it's kind of like if I put light on a moving sidewalk, is it going to move faster than light not on a moving sidewalk? Okay, so they were kind of thinking the Earth itself was the moving sidewalk through the sort of space out here, right? Anyway, so that was the Michelson-Morley experiment, one of the most important experiments in history that people sometimes say as well, right? Anyway, so there was that guy there. There was some other guy. The guy who actually measured light was this guy, Romer. I don't know how to say it. This is a pretty cool experiment as well. Basically, what he did is he had Jupiter here, and then he had the moons of Jupiter, a moon of Jupiter, kind of going behind here, okay, like that. And based on how long it took, or how long it was behind the shadow, right? For example, was very, it was the same all the time. So if this moon entered the shadow of Jupiter, because here's the sun over here, sorry. If this moon entered the shadow of Jupiter, it would exit the shadow of Jupiter at a very predictable time, okay? So you would know that time. Then the question was, well, okay, how our observation, so let's say we've got, then if we observed this happening from this side of the Earth, so you could kind of still see this thing exiting from the shadow, versus if we observed this happening from this side, because now Earth, remember Earth rotates, right? In this scenario, Earth is moving closer, right? And in this scenario, Earth is moving further away, okay? So what he was able to do, basically, at this point is say, well, he noticed that in this case here, it appeared that the length of time that the moon was behind Jupiter was longer. And the reason why it's longer is because as the thing exited, it's traveling through space, right? But then during this travel period, the Earth itself moves a little bit. So in the end, it has to travel a little bit further, okay? Whereas over here, on this side, the moon exits, right? And the light, as it exits, it starts to travel. It travels in every direction, right? The light that's now reflected. But we're interested in the light that then travels to the Earth, okay? But during this period at which it travels, okay, the Earth actually moves a little forward. And so he was noticing that, so when the Earth is moving towards this, it appears that the moon is behind the shadow less, versus when the Earth is moving away, it appears that the moon is behind the shadow of Jupiter for a longer period of time. And he says, well, that's impossible. The direction of motion of the Earth doesn't slow down this moon. And so the only explanation for it is that the light itself actually has to travel through space, okay? And so it has to travel further in this, and then this is closer. It has to travel further versus not as far in these two different scenarios. And then what he did is he took those time intervals and he knew the distance between the Earth and the Sun, and the Earth and the Jupiter, and Jupiter and the Moon, and Jupiter and the Sun. He knew all these distances, right? And what he did is he just did some calculations based on the times and the distances, and he was able to extrapolate the velocity of light, okay? Because, things that move at a constant rate, velocity equals distance over time, okay? And so he was going to be able to say, well, this distance is such and such, that distance is so and so, and I know that this is an observed length of time difference, and so therefore he's able to determine the velocity of light. Pretty cool. That guy's name was Rower or something like that, Romer, and there he goes. All right, so that was a cool little experiment. Now, let's see, what are we looking at now? So now we're talking about Einstein's special relativity, right? So, based on all this stuff, right, and the fact that based on Michelson's Morley's, or whatever this guy's name is, Morley, based on these guys' experiment here, Einstein was saying, like, look, it appears that light just travels the same speed for like everybody, for the whole world and for everybody who's viewing it, right? And so this whole idea of, shooting light on an Earth that's moving through space doesn't speed the light up. Einstein's conclusion is that the speed of light is constant for all observers, regardless of whether or not they are themselves moving. Okay. This was then a huge, big deal, right? In fact, here it says mind-boggling, right? So this statement here, as I've already said it means that if we're standing still, the speed of light will be this speed, measured by Romer, more or less, but it will be exactly the same for everybody watching it, even if you're moving through space at 1,000,000 miles an hour, right? So the speed of light is constant for whose value is not measured with respect to the frame of reference, okay? All right, so there we have it, right? So as a result, basically, Einstein sat on a bench and started thinking about this. He's like, well, wait a minute, how is this possible? Then if that's the case, then what needs to adjust for different viewers is the actual time that has passed for the viewers. In order for this light to be observed moving through space at the same velocity for two people who are moving at different velocities, then the two other things in the formula, velocity equals distance over time, these guys apparently must adjust. Okay? And so that's kind of what his little conclusion is. So it can be shown that the time does adjust. And we end up with these formulas here. These are the formulas that dictate the relationship between the two time intervals that pass based on two different people who are moving at two different velocities, right? And it's actually apparently true, right? So if I'm skirting along at 500,000 mile an hour and somebody else isn't, and we both look at the same event, right? Just remember, what does time measure? Time measures the length of time. It's a tough one to say without using the word time. The time is basically measured. It's like, well, how many ticks of a clock happen during a certain event, right? And that's how what we're going to try and see. So these events could be whatever, maybe like I don't know, somebody shooting a basket on in a basketball game. They shoot and the basket goes in there. Now I look at my watch during that whole thing, and maybe 3 seconds go by while that ball is in the air. Okay, somebody else looks at that event, and for them, maybe 2 seconds go by. You might be saying, well, how is that possible? It's the same event. 3 seconds go by for one person and 2 seconds go by for another. The only way that this is possible is if the two people observing that event are moving at different velocities with respect to each other. All right. And so that's the result of Einstein's theory here. Okay. And what we're going to now do is I'm going to pause the video, or I'm going to send this in a separate video. I'm going to go ahead and explain these two formulas here. But what I've just done now is just sort of like an introduction to the origins of these videos here. These formulas. And so there it is. We're now going to go ahead and explain these two here. Oh, by the way, I didn't talk about the length one here. It also means that length, all right, changes as well. So what are we talking about? What does length do? Length is a way to measure the distance between one point and another, right? And so if I hold up a pen and I say, well, the distance between the tip of the pen and the other tip of the pen is 3 centimeters, okay? Well, no, that's silly. No pens are 3 centimeters long. Let's say it's 20 centimeters. No, whatever. 10 centimeters. We got a 10 centimeter pen here, and that's a measure of length. Okay. Now the question is that pen is just sitting there from my perspective, but if this pen is zooming by, the same pen is zooms by me at a particularly high velocity, and I attempt to measure its length, it will appear not to be 20 centimeters anymore. It will appear to be actually less long, okay? And the reason is because of the time interval change thing as well, right? And so the difference in basically it has to do with the idea that the ratio of the time and the length needs to maintain a certain value, okay? And so yeah, let's go ahead and explain these formulas with a geometric proof in the next video. Let's go.